I'm going to go over the homework for this week today, and this will be basically just like what we usually do in office hours, but in advance. Yeah, and then I'm actually going to record this one and I think host that as the office hours. So probably just do office hours this week or something. And quizzes will resume next week. So the homework this week is on chapter 13. Chapter 13 has to do with universal gravity, which is like the gravity that occurs in outer space. Up until this point, gravity has just been m times g. And that g, that negative 9.8, or g equals 9.8 meters per second squared, is doing a lot of heavy lifting for us. Basically, the assumption in every problem you've done until this point in the class has been that you are very near the surface of the Earth, and that's been fine so far. But now what we'd like to do is go ahead and formulate a more robust presentation of the actual gravitational force. And the one motivation that I'll give you all for this week is that this is what physics 2 is going to look a lot like. And there are a few problems in here that you will do again in physics 2, but there you'll use the electric force. But the electric force is going to function similarly to the gravitational force. All right, so if we were to just go into space, we have two particles, M1 and M2. And we're far, far away from planet Earth. There's going to be an attractive force of gravity between these two particles. And that force of gravity is going to be big G mm over r squared. It's typically the way you'll see it written. This is the way that I will always write it. Sometimes you'll have G m1 m2 over r squared. But oftentimes we're dealing with a planet and then an object way out in space. And in that case, big M will be your planet, little m will be the object out in space. So this is the formula that I'm going to use. The constant G is, let's go ahead and write it up here, 6.67 times 10 to the negative 11. That's just how we tell the formula how strong gravity happens to be in our universe. It's not very strong. It's the weakest fundamental force. And the one other variable here is the r, which is just going to be the distance. And the one thing that I'll mention now, this will come back up in a few problems, is that this r is the distance between the center of mass of each of these particles. So that will come up when you have a planet, for instance, with a radius and some mass distributed. For the problem that we have here, they're going to give you, for problem number 1, they give you a force and they give you the mass of the two particles. And they ask you to solve for the separation that produces a given force. So in that case, you're just going to solve this equation for r. Since r squared is on the bottom, you can switch it with the force of gravity. And of course, we need to take a square root, and we get that r is the square root of g big M little m over the force. Which one is big M, which one is little m? Doesn't really matter. You notice that they're multiplied together. That also tells us that these forces will have equal magnitudes. And in general, you're just going to calculate the magnitude of the force with this green equation, and then you'll just assign the direction using a picture. Keep in mind this is a vector, so vector summation rules apply. Like for instance, in the next problem, problem number 2, we're going to have a setup of 5 different point masses. And we're going to need to calculate the gravity on the central mass. So we have a square with a given side length, and we're asked about the gravity on the central. So we have 3 masses named 1, 2, 3, and 4. Each mass will exhibit its own force of gravity on the central mass according to GMM over r squared, and it'll be an attractive force. So if you'd like to practice, you can label all your forces and draw their directions. Particle 1 will pull the mass up to the left. Particle 2 will pull the mass up to the right. Particle 3 will pull the mass down to the left, and particle 4 will pull it down to the right. I mentioned it, but just for consistency, that central particle is called particle number 5. M5 is its mass, and we're actually trying to solve for M5. Now, our force of gravity equation, G big M little m over r squared. Force of gravity equation tells us that so long as the mass of each particle is the same, then these forces would cancel out. Now, we can sort of generalize here and say that if I wanted to calculate the force from any one of my four particles, that would be equal to G times the mass of that particle, that's what I'm saying, m sub I, times the mass of particle 5, over the distance squared between them. What is the distance from any corner of a square to the center of a square? The diagonal of the square is L root 2, which means that the distance from the corner to the center is L root 2 on 2. I don't know why my hand doesn't want to do square root. L root 2 on 2. Cool. So on the bottom down here, you'll have L root 2 on 2. Now, in the problem, they give you the masses of 1, 2, 3, and 4, and they're all different with the exception that 1 and 4 have identical masses, and 1 and 4 are on opposite corners, which means that the forces of gravity due to each of those particles are pointing in opposite directions. And since their masses are the same, and of course the distance will be the same for each of them, that's going to mean that these two forces will cancel out. So we need to give the x and y component of the net force on particle 5. Yes, we're given M5. I think I said a second ago that we had to find it. We're given M5, we need to find the x and y components of the force on 5. So the force on 5 is going to be just due to F2 and F3. And we know how to calculate them right here. I can just write them out real quick. F2 would be equal to GM2. Oh, forgot a square right there. GM2 M5 on L root 2 on 2 squared, which is going to be L squared on 2 on the bottom. Yeah. And then F3, man, I don't know why my hand's not listening. F3 will be GM3 M5 on L squared on 2. Okay, now in order to add these forces together, keep in mind these forces are vectors, so we need to do a vector sum. Ultimately, we're just responsible for providing the I hat and the J hat, and here's how you'll calculate them. The I hat component will just come from the two x components. So F2 points up and to the right in the first quadrant. That means it's going to have a positive x component and a positive y component. Force 3 points down to left, so there'll be a negative x and a negative y. That means that your I hat component is going to be F2, where you'll calculate F2 right here, cosine of 45, minus F3 cosine of 45. Those are just your x components, vector summed together. And the y will be F2 sine of 45 minus F3 sine of 45. Since sine and cosine of 45 are both root 2 on 2, those will be identical. And yeah, so your answer will be the same for both in this case. Okay, so that's kind of the last, well, we'll come back to point masses when we define some other topics, but what we're going to talk about for just a little bit here is going to be some distributed mass type problems. So problem number 3, we're going to have this sphere, but they're going to cut out a section of the sphere. Let's take that one more time. Got a sphere with a section cut out of the sphere. And there's the center of the sphere. So the section that is cut out has a diameter that's going to be equal to the radius of the sphere. All right, that'll come in just a second. Ultimately, what we're looking for is the force of gravity on this little point mass all the way over here that we call M. And they tell us that the distance between the center of the sphere and the point mass is a distance d. So we're given the radius, we're given the distance d, we're given the mass of the sphere before they cut this chunk out, and we're given the mass of the point mass. Now, the fact that they only give us the mass of the sphere before the chunk is cut out is a little bit of a hint of where we need to go. But what I'll say right now is that the force of gravity is still going to be gmn over r squared. However, there's a little bit of strange geometry going on here because the chunk that was cut out is not centered. So that means that there is mass that is closer to the point mass that is missing. So the force of gravity is going to be a little bit less than you would expect if you were to just cut out some mass from that sphere. But what we could do is we could just find the force of gravity due to the entire thing and then subtract it out. So that's what we're going to do. Our total force of gravity will be equal to the force of gravity due to the sphere minus the force of gravity that we lost when we cut out that chunk. The sphere calculation will be pretty straightforward because we're going to be given the mass of the sphere, the mass of the point mass, and we know that the distance, which is the center mass distance, is d. So this is just g, big M, little m over d squared. That would have been a simple calculation, but we had to subtract out the chunk. So how are we going to do that? Well, as I mentioned when we first started the problem, the chunk that is cut out has a diameter that is equal to the radius. That means that the radius of this chunk is r on 2, half of the radius of the entire sphere. Why is that important? Because we know that the constant here is going to be the density. The density of the sphere is going to be the same as the density of the chunk. And density is mass over volume. We know the mass of the sphere is that constant big M that we've already input right here. So we'll keep that as the mass. We have to do mass divided by volume when we're dealing with the density. The volume is 4/3 pi times this big R cubed. And this has to be equal to the mass of the chunk over the volume of the chunk. And the volume is going to be 4/3 pi r squared. Think about what the r is. If it has only half of the radius of the entire sphere, that'll be big R on 2 cubed. And if you were to solve this, you get the mass of the chunk is equal to 1/8 of big M. Everything else will cancel out. And it sort of makes sense because the radius goes with the cubic, or the volume goes with the cube of the radius. So it makes sense that half the radius will give you 1/8 of the mass. All right, so now that we have that, we can go ahead and plug it in to this equation. We want to do gmm over r squared. All right, so I have g. Big M is always the mass of the planet that's doing the attracting, which in this case we have 1/8 times big M. We will have little m, that'll be the same. And then we have to divide by the distance. We need a center of mass distance from the point mass to the center of the chunk. We know that the whole distance is d, and I know that this little bit is a radius of the chunk, which we know is r on 2. So that means that the total distance would be d minus r on 2, and that whole thing will be squared. You can factor some stuff out before you plug this into your calculator, but ultimately this is going to be the total force. I'm going to come back to this problem to set up a different problem. But one thing I want to point out here is that we made this problem more difficult than just a gmm over r squared by moving the mass around and putting it in a different kind of shape. We're going to do something a little different to make the problem difficult in just a second. But before we do that, we have a kind of one-off problem here, problem number 4. We have a neutron star. A neutron star is just composed of neutrons. You have a star that goes supernova that isn't large enough to form a black hole like our sun will do. Actually, I don't even know if our sun will ever undergo that process. Anyway, point is, you don't get a black hole, you just get a neutron star, which isn't as dense as a black hole, but it is very dense in and of itself. And as a result, for instance, the mountains on a neutron star are said to be like millimeters high because it's so dense, there's so much mass, the gravity is so strong that the neutron star holds on to all of its mass. However, it's going to rotate very quickly. And in this problem, they give you a rotation speed, which is an omega. They tell you it's like 1.6 revolutions per second. The reason I'm writing it out, because I want to point out that we still need to work with radians, not revolutions. So you want to multiply by 2 pi. And we're given the radius of this neutron star is 39 kilometers. Again, writing it out because I want to point out that you need to multiply by 10 to the third. All right, and what we're going to do is we're going to spin this neutron star as fast as we possibly can, so fast that the material on its surface is about to fly away. So what's going on here is you have this star that's rotating, and we know that there are two types of acceleration. We have our tangential acceleration, and we have our centripetal or radial acceleration. And in this case, we want the radial acceleration to keep the neutron star in place. Now, you notice I'm talking about accelerations, all we talked about so far is force. Remember, F equals ma. The force of gravity for the universe is g big M little m over r squared. It's equal to ma. Cancel out the little m from both sides, and we get that the acceleration due to gravity is equal to g big M on r squared. It's a very useful equation. Now we cannot say the acceleration due to gravity is just negative 9.8 in the y direction, right? But this will give us an acceleration due to gravity so long as we pay attention to how our mass is distributed and how our distances work. In this case, though, it's very straightforward. We want our acceleration due to gravity to provide the centripetal acceleration on the neutron star to keep all of the mess that's tied up in the neutron star. And so in this case, we simply set our centripetal acceleration equal to our acceleration due to gravity. We have two definitions for centripetal acceleration, v squared over r or omega squared r. We're given omega and r, so we'll do omega squared r is equal to g times big M on r squared. And they're asking us about the mass. They just need to solve for mass. Mass is going to be equal to omega squared r cubed on g. Question? Sorry, was that one more time? Can you repeat why the centripetal equals those rotations? Yeah, so this neutron star is spinning so fast that if it were to spin any faster, the speed of the rotation would cause the matter to start flying off of the star. So the thing that is keeping the matter attached to the star is the force of gravity, right? Or the acceleration due to gravity. And since it's rotating, since the matter is rotating around the edge or the surface of the neutron star, that's a centripetal acceleration. Yeah. Okay. Next one, problem number 5. Yeah, okay, so problem number 5 is gonna, we're gonna have a planet that is composed of two shells, kind of like a planet Earth a little bit. We're gonna kind of simplify it a little bit. Planet Earth has a core that has some matter, and then it has a mantle, and then there's a crust. But I guess here we're just gonna have a mantle. I probably should make the mantle red, but I am not a geologist. In this specific problem, they tell us that the inside has a mass m and a radius r. And the mantle type thingy has a mass of 4m and a radius of 2r. And they're going to ask us about the acceleration due to gravity. So let me just write it down. We just use it, but just to remind you, our acceleration due to gravity is g times big M over r squared. Now, what they're actually going to ask us to find is the acceleration due to gravity at two different points. The first one, the more interesting one, I think, is that they ask us to find the acceleration due to gravity at a point that is a distance r from the center. In other words, at the very edge of the core, before you go into the mantle, what is the acceleration due to gravity right there? And you can do kind of a drawn out proof here, but the long and short of this process is that all the stuff that is outside the core, if you are at the edge of the core, all the stuff that is outside of the core is going to cancel each other out, because you have some stuff right here that's going to cancel, it's going to pull you in one direction, then you have other stuff that's a little bit further away. So even though there's more of it, it's further away. And the result is that it's going to cancel. It's a very hand-wavy explanation, but it's good enough, I think, for us to do this problem. Yeah.
Is the logic that inside any spherical object, the net force is?
If you're like in a hollow center.
Inside.
Yeah, if you're in the hollow center. So yeah, you can think about if there was no core and you're just floating around, you'd just be floating around, right? Because everything around you is floating. Now, what we do need to, the terminology that we need to get used to is that from the center of mass of the object out to the point that we're investigating will form a radius of a sphere. And this sphere is just a geometric sort of tool. It's called a Gaussian sphere. You're going to do a lot more of that in physics too. What you need to know is that the only acceleration that we'll have is due to the mass that is enclosed within that little sphere that I've drawn. So I'm going to write that right here. We're doing g times the mass that's enclosed over r squared. For this problem, our mass that's enclosed is just big M. They tell us explicitly. So for part A, our acceleration due to gravity is just g times big M over our distance big R squared. That's it. Everything there is given. For part B, they're going to switch it up a little bit. Now they're going to put you at a distance 3r from the center. So now we are all the way out here. And since we are now outside of the mantle, it means that we're going to experience the gravity from the core and the gravity from the mantle. But again, we can use the same idea of generating a sphere and looking at all of the mass that we can enclose with the sphere that is generated by that radial vector. So for part B, again, our acceleration due to gravity is going to be g times the mass enclosed over r squared. We have big G. What is our mass enclosed here? Yeah, good. We have m for the core plus 4m for the mantle, which gives you 5m. And then the r on the bottom is just your distance from the center of mass. So in this case, we're all the way out at 3r. So we just have a 3r squared. Okay, so far so good. Make sure they get that down. We're going to carry this idea over of enclosing mass. And the same argument is going to work with force of gravity, which is what we're going to have in the next problem. So problem number 6, we have an apple, and we're given, we got like a planet, and I don't know why it's an apple. I guess it could be anything else. That's fighting for my life. So this apple is at the surface of the planet, and it has a force of gravity that they call F sub big R, I guess to indicate that we're at big R, the radius of the planet. And they're going to give us a ratio. They're going to say, all right, you can either move this planet out into space or into the planet, and you want to find out where you get the certain ratio. So for example, they may say, like, where is the force of gravity equal to 0.5 times the force at the surface? And there's two answers. The first one is, I think, a little bit easier. we are going to move. Okay, we need to get these distances from the surface. So I need to do that at the very end. But part A, we're just going to move out into outer space. So for part A, we move away from the planet. In that case, we just have our force of gravity. We just work right off of this equation. So our force of gravity is G times big M times little m over little r squared. We want that to be equal to 0.5 G times big M times little m over big R squared. Everything cancels. And you'll get that R is equal to the inverse of whatever your ratio happens to be under a radical. So for me, that would be square root of 2. Yours might not be like a nice even fraction, but it'll be root 2 times big R. Now, this is a distance measured from the center of the planet. The problem itself is going to ask for your distance from the surface. So your distance from the surface will be equal to whatever this little r is minus 1 big R. That's just as a side note. And that's going to be the same thing's going to hold in part B. In part B now, we're going to drop the apple into an imaginary tunnel and let it fly toward the center of the Earth.
Wait, is the small r the distance from the center of the planet out to outer space?
Small r, here, let me draw a pic. Small r goes from here out to here.
Oh, yeah.
They want to know this right here. I probably could have called it H instead of D, but they want to know the distance from your point out in space to the surface of the planet. Cool, okay. Part B, we're going to drop the apple, into the planet, and it's going to land somewhere inside. And we're going to do the same thing we did in the last problem. As it goes into the planet, there's going to be a little imaginary Gaussian sphere defined by r, the distance from the center. And again, within that sphere, density is going to be constant. So our density enclosed is equal to our density total. Our enclosed density is the M enclosed, which we are after, divided by the radius enclosed, which is 4/3 pi little r cubed. This has to be the same as the total density of the planet, which is the total mass, big M, over the total volume, which is 4/3 pi times big R cubed. And I'm going to give you a relationship that you can use anytime you need to solve a problem with a sphere like this, which is the mass enclosed is equal to M times little r cubed over big R cubed. Plugging that into our force of gravity equation before we actually solve this problem right here. We'll come back to that in just a second. But we can plug this into G big M enclosed times little m, that's a G, over R squared. Plugging in our enclosed mass, we're going to have an R cubed on top and an R squared on bottom. So what do we get? What are we going to actually end up with? We'll end up with G times big M times little m times R over big R cubed. And this right here will always be your force of gravity inside a spherical planet. It can give you a planet of some other shape, but that's typically going to be reserved for physics 2 and beyond if you keep going. All right, so in this problem, this is going to be the force of gravity that we're going to plug in on the left side of this equation. We'll set it equal to 0.5 times the force at the surface. So that gives us G big M little r over big R cubed is equal to 0.5 times, same thing we have on the right side over here. Big G, big M, little m over big R squared. Just about everything will cancel except little r is equal to 0.5 times big R. Again, you're going to have a different ratio So in this case, my D happens to be equal to my little r, but remember that you then need to plug this into the distance inside the plant from the surface is equal to little r. I'm actually going to flip the sign, big R minus little r, because it's a positive distance. But just make sure you plug that in at the end. Okay. Now, I think this is kind of the last topic. We actually do have one more topic that we're going to investigate. Oh, is everyone caught up on that? Sorry. Cool, good, okay. The last sort of fundamental physical topic that we're going to redefine here is going to be potential energy. So from before, we had a force mg that is associated with the potential energy mgy. How did we get this? We took our force of mg and just multiplied it by the distance. And that was kind of it, right? In this case, we have to be a little bit more particular with how we define our force of our potential energy. And specifically, we need to use that the work is equal to the negative change in potential energy, and that the work is also equal to the integral of F dotted with dr. Maybe a little more technical of a definition than you've seen. I think you've done the integral of f of x dx, right? Which is just a one-dimensional version of that definition. I think you're good enough to rely on this. Point that I need to make here is that notice we have a negative sign on the potential energy. Also keep in mind that we're going to be integrating, for the force, you don't have to write this down, we're going to be integrating gmm over r squared. When I integrate a 1 over r squared, I'm going to end up with a just an r to the -1, or an r, just a single r on the bottom. And I'll have a negative sign. And yeah, so anyway, the point here is that this is why it's important when you're using, let me write it off to the side. No. Ooh. Well, why? What have I done here? It's important when you're using potential energy due to gravity for point masses that you have a negative sign out in front. That's my entire point. And it's going to be G big M little m over just a single r. Okay, that's the equation. Probably shouldn't have gone that far into trying to hand wavily derive it there, but the rules for gravitational potential energy is that for each pair of masses, there will be a potential energy stored between them. And the negative sign tells you that when we're far away, we have more potential energy. And as R decreases, there will be less and less gravitational potential energy stored. That's what the negative sign very generally is going to tell us. So in this problem, problem number 7, we have an arrangement on the XY axes with 3 particles. We have particle A, which is free to move up and down the y-axis. And then we have B and C, which are glued to the x-axis. And there's a graph that you kind of have to read, kind of. You have to read it for one note, which is that for second part, we have to read the graph. For part 1, they just want to know the masses of B and C, but they tell you that as A moves infinitely far away, you approach some asymptote that's given to you. Asymptote. And I definitely spelled that with two S's. They give you an asymptote of the graph as particle A is removed from the arrangement, basically. And that asymptotic value for the potential energy is the potential energy when you just have B and C present. Since B and C are the only things present, for part A, you just set your asymptote value, which I'll just call the given potential energy. You just set it equal to negative G M sub B, M sub C over the distance between them. And the distance that's given in the problem is this distance here. They say that these are both d. You don't need to copy that down because you have it when you're doing your homework. But that means that your total distance between these two is 2d. Now, ultimately, in this part, you want to solve for the mass of B and C. You're told that they have identical masses. So in order to proceed to a solution, you just replace this with some m squared and solve for whatever that m is. For part B, we're going to use the other extreme of the graph, which is that we take A and we're going to move A down to the origin. And when A is at the origin, we can read off of the graph that when y is equal to 0, the potential energy is negative 3.5 times 10 to the negative 11 joules. This is a total potential energy for our arrangement. And yeah, so in general, I have 3 particles. That means I have 3 potential pairs for the particles. That means that my total potential energy is the potential energy between A and B, plus the potential energy between A and C, plus the potential energy between B and C. Each pair gets its own potential energy. Each potential energy is calculated with this equation right here. Now, we already know the potential energy from B and C. That's the asymptote that we used in part A. So you'll just plug that number in there. Similarly, we read this number. This number will be the same for everyone. It comes off the graph, and they're not going to change the graph. So that will go on the left-hand side. The only thing we need to deal with then is these two. You'll have some number over here, and you'll have some number over here. In the middle, we have these 2 terms. They're going to be identical terms. The reason they're going to be identical is because they're each going to have a mass for A, and then the other mass will be the B and C mass, which is identical. So for each of them, you'll have negative G m sub A times the m you found in part A over the distance from the origin to each of the masses is just a d. And so you just have 2 of these m sub A times m over d. Make sure that you have negative signs on the numbers that you plug in here. And you can combine these 2 together. You just have 2 GMM over d's. And then you can solve from there for the mass of particle A. All right. For problem number 8, we are just this is kind of a conceptual problem. They ask us for the relationship between a couple of different variables and the radial distance. And we just kind of need to run through them. So the first one asks about the period. The period is the time that it takes to complete 1 revolution, which is important when you're talking about satellites and planets and stuff like that. And this comes from something called Kepler's law. And Kepler's law tells us that the square of the period is proportional to the cube of the radius. And since we need to find the rate at which the regular period varies, you take the square root of both sides. We get that the period varies with r to the 3/2. And your answer in this problem is just going to be whatever the exponent is on r.
Does period use the same variable as like then they were both T?
Yeah, big T is period. Yeah, it's all, I know it also gets repeated for tension, but we won't have a tension when we're doing universal gravity at least. Part B, they ask about the kinetic energy. Well, I know that the delta K is equal to negative delta U. And that's good enough for me because I know that U varies with 1 over R. That's R to the minus 1. And since K and U have to be on similar terms, this is the same as K varying with R to the minus 1. For part C, they ask about the angular momentum. I'm actually going to do part D first. Part D asks about the speed. For that, we'll use our answer from part B. I know that K varies with the speed squared. And I know that it also varies with R to the minus 1. Take the square root of both sides, we get that V varies with R to the minus 1/2. For part C, where they asked us about the angular momentum, it's back. Angular momentum is mRV. Of course, there's the perpendicularity, the cross product, and all that stuff, but we just need to kind of figure out how this stuff all varies. And we know that this will be R, and then V will vary with R to the minus 1/2. So we have R to the 1 times R to the minus 1/2, which is R to the 1/2. And there's your answer there. Okay, we've got 7 minutes. I think I can get through the last 2 problems. We might run a little bit over, but at least this way I can post this recording. Okay. Problem number 9. Problem number 9, we have just an object in orbit around the Earth's surface. The first part is they ask us about the linear speed necessary to be in a circular orbit at a given altitude. So they're asking about the linear speed of our orbit. And we could do this a few different ways, but the most straightforward way is going to be to just say that we have just like with the neutron star problem, our acceleration due to gravity is equal to the centripetal acceleration. Our acceleration due to gravity is still going to be g times big M over little r squared. On the neutron star problem, we had an omega, so we used omega squared r. And this problem, we're asked for v, so we'll do v squared over r. And then if you'd like, you solve for v. V is equal to square root of g big M over little r. You'll plug in r, you'll plug in g. You're supposed to look up the mass of the Earth. One thing that I will mention is that your radius on the bottom has to be the radius of the Earth itself, which is 6.37 times 10 to the 6th, plus the h that they give you. They're going to give you a height off of the Earth, 125 kilometers per mile. You have to add in the radius of the Earth. I'll also mention, because they're not going to give it to you, that the mass of the Earth that they expect you to use is 5.98 times 10 to the 24th. Part B is just going to ask for the period. Period is 2 pi r over v. That's our very first definition of period, way back at the beginning. And you'll just plug in your v. You can simplify if you want to, or you can just plug in the value that you get here and plug in this R again on top there.
No.
Yeah, I think we're probably ahead. Okay. Let's see if we can get through the last problem, and then at least you'll have your homework done for the week. All right, last problem. We have two satellites, A and B. They're both satellites of Earth. They have the same mass, and they're launched into circular orbits at two different altitudes. And they ask about the ratio of the potential energy, first of all, between satellites B and A. So they say we want the ratio of the potential energy for satellite B to the potential energy for satellite A. Most of this problem is just a question of what's going to cancel out. For satellite B, we have negative G mass of the Earth times mass B over the distance. Now they're going to give you an altitude and an Earth radius. So that distance will be the radius of the Earth that's given plus the altitude. I'm going to call that H for particle B. On the bottom, we have negative G mass of the Earth, mass of A over the radius of the Earth plus the height of A. They're going to have different heights or different altitudes. What will cancel here? My G's will cancel, my mass of the Earth will cancel, and since they tell us that these guys have the same mass themselves, M sub B and M sub A is going to cancel as well. Excuse me, we're going to get R sub E, radius of the Earth, plus H sub A over R sub E plus H sub B. For part B, they ask us for the ratio of the kinetic energy of B to the kinetic energy of A. Does anyone want to take a guess? We know that delta K is equal to negative delta U, right? So the negative signs will just essentially cancel out. And that tells you this is the same as the answer we get from part A. Part C, they ask which satellite has the greater total energy. They give us the mass. We're in charge of finding the energy. One thing that I'll just point out from the very beginning is that it's the satellite which is furthest away that has the greatest potential energy stored, right? So as a result, it's just going to be whichever has a bigger altitude. And then the last one, they ask us to find the difference between the two energies. So I'll just give you the equation for this, and then we'll go ahead and close it up. The difference, first of all, the total mechanical energy, adding together kinetic energy and the potential energy, total mechanical energy is negative G big M little m over 2R. So in this problem, you just need to find the delta E, which will be the energy from B minus the energy from A, which once I factor out all of my common stuff, will be G big M little m over 2 times 1 on the radius of B minus 1 on the radius of A. All right, and that's it. If you have any questions, feel free to come on up. And yeah, likely will not be.
It's just the, that it